Hello, everyone. Um, so we're going to start the section 12, graphics. We're going to have five presentations here, very interesting topics, and I hope yeah, all of us enjoy this section. I would like to ask people to send questions to YouTube because I'm facing some issues with Wova. So if you have any questions for the speakers, please uh, place the question in YouTube, and then I will be more than happy to uh, forward this message for the speakers. Okay, so um, I believe we are a little bit late, so let's start right now. I believe Jean is going to make this presentation.
Hi, my name is Jean Paulo Vieira de Mello, and I'll present the work entitled Deep Traffic Light Detection by Overlaying Synthetic Context on Arbitrary Natural Images, produced by me, Lucas Tabellini, Rodrigo Berriel, Thiago Paixão, Alberto de Souza, Claudine Badwe, Nico Sebe, and Thiago Oliveira Santos, and accepted for publication by Elsevier Computers and Graphics. The interest in using deep neural networks for autonomous driving is rising recently. By training a network using real-world traffic images, it is possible to detect and classify elements such as pedestrians, traffic signs, traffic lights, and others. Particularly, detecting traffic lights is important for the vehicle to avoid accidents. However, collecting and annotating real-world data is laborious and subject to imbalance, since the yellow state is less likely to be captured. We propose a solution which involves using arbitrary images containing natural scenes as backgrounds, producing simple three-dimensional synthetic traffic contexts as foregrounds, combining them, and training a deep detector, so that a model trained with no efforts on assembling real-world datasets can detect the traffic lights and identify their states successfully. Those are the quantitative results obtained for the experiments performed to access our method. The first results show that the whole context has a positive impact on the model's performance, against training with only the 3D traffic light models as foregrounds. Then, it is seen that training with such 3D models is more effective than replacing them by 2D templates. The next results show that training with negative backgrounds, which are traffic-related images that do not show real traffic lights, is reasonably effective. Meanwhile, positive backgrounds, which thus show real traffic lights, can impair detection. Also, using the proposed method as data augmentation yield good results, especially when mixing synthetic and real-world data instead of performing fine-tuning. And finally, it is seen that our method and a model trained with real-world data present comparable performance. This video shows the qualitative results obtained with the proposed method and compared with a model trained using real-world data. The first test dataset is IERA, our proprietary dataset. We also evaluate our results on the publicly available datasets LISA, Udacity Driving, and LERA. You should have noticed that common mistakes happen, especially when some lead headlights appear and are detected as traffic lights. Now you see part of the LISA dataset. As you can see, they perform comparably, detecting and classifying successfully most of the traffic lights. Udacity dataset is recorded in a low frame rate, and that's why the sequence seems to be a bit accelerated. Even so, it is possible to notice that the traffic lights are well identified. Note in this example from Lero dataset that the yellow traffic lights are well identified as well. For the real-world reference, we have done an oversampling of the yellow samples. This was not necessary for the proposed method, as the dataset was generated with a balanced number of yellow, green, and red samples. As you can see, our method performs comparably with real-world modeling, with a much smaller effort on assembling the training dataset. Also, the method enables the generation of a naturally balanced dataset, which can be built in infinity ways, as the researchers are free to model the traffic lights and contexts as they wish. This ends the presentation. Thanks a lot for watching.
Okay, thank you, Jean.
Hi.
While we waiting for questions, let me ask you my question. So, um,
Okay.
uh, can you please give us a little bit of more details about the architecture you are using? I'm assuming you are using a convolutional neural network, but which exactly architecture are you using?
I have used the faster RCNN with the background of ResNet 101.
And did you face any issues with the training process? How much you have to tune it to make it work properly?
Sorry?
Uh, have you faced any issue with the training process? What I mean,
Yeah.
have you, for example, to introduce some noisy beyond, the background and so on? So, can you give a little bit more details about the training process? Well,
Yeah. First, the was to use just templates of traffic lights, not the whole context of traffic. And but this yielded a problem that tail light and other lights in the scene or other details similar to traffic lights were often confused by traffic lights, and so we had to make this evolution to the project to make to put the whole scene, the whole light. So the main phases there it was this the confusion of traffic lights with other lights and other small details in the scene, because traffic lights
okay,
are very simple.
okay, thank you. We have a question here from Joaquim Bento. He's asking you if you only test your system in daylight images, or have you also mixed it with, for example, images during the night and things like that?
No, we just tested in the night. At night, we didn't test.
Okay, another question. Joaquim Bento again. Did the luminosity affect the method?
Well, actually, we tried to an image, but too little. We didn't spend much time on this, and we've noticed that it was a bit harder because every spot of light in the image was interfering in the process. So the luminosity of the day helped it to differentiate other lights from lights from the traffic lights, right? So
Okay, I think we missed you a little bit, but I think we already had enough questions here, so let's move on for the next presentation. Thank you very much, Jean.
all right.
Hi, welcome to this short presentation of our work bounded by harmonic blending of Möbius transformations for flexible omnidirectional image rectification. The goal of our method is to correct distortions in omnidirectional images, which are images of the full spherical field of view around a viewpoint. The most noticeable distortions are straight lines in the world appearing bent in these images. Here is an output of our method with the lines rectified and the full spherical field of view preserved. We achieve this result with the help of a user who specifies in our interface geometric handles over the image, such as these curved line segments in red that should be rectified and the areas inside the white polygons that should stay fixed. The result of our method shows how it is successful at achieving the goals specified by the user. We give the user the possibility of specifying bone, point, and cage handles. For each type of handle, our method defines 3 meaningful points, and their new positions on the sphere define a unique Möbius transformation that will be associated to this handle. We combine the multiple Möbius transformations into a single result using the bounded by harmonic weights due to their locality and smoothness. We also give the user the possibility of automatically rectifying all lines by collinearizing their middle points and their endpoints. While this works well for some cases, in cases with many lines, this strategy leads to this bad result, caused by the independent rectification of multiple lines. To overcome this problem, we propose an energy minimization formulation that repositions the handles on the sphere in a way to preserve as much as possible their initial relative positions. This methodology leads to successful automatic line rectification. Please refer to the paper for more details about this minimization. Our methodology was implemented in MATLAB, and the interface was developed with the Guides toolbox. The program is divided in 2 windows. The first window is where the user defines the geometric handles that will act as boundary conditions in the bounded by harmonic weight computation. In this example, a total of 27 bone handles that are shown here in red are specified by the user. The first window also allows the user to specify bone, point, and cage handles, but in this example, only bone handles were used. In the second window, the user can edit each handle individually, but opted for rectifying all lines at once in this case. In this example, the use of a point handle allows to zoom in the red car and makes it possible to read the license plate without losing sight of the rest of the area, what can be useful for surveillance applications. We can compare our methodology to the one developed by Souto Ferreira and colleagues in 2017 in this fairly complex setting, with a considerable number of lines to be rectified. Although their method rectifies most part of the lines, their extremities are distorted due to the overlapping of transformations that occur in these areas, as shown in the left inset. Also, Gaussian or rectangular regions are not versatile enough to handle lines with such proximity. On the other hand, our method generates weights in a way that the transformations do not overlap and the transitions between them are smooth enough to be able to rectify lines that share endpoints. We also compare our methodology to the one by Carroll and colleagues in this outdoor setting, with the goal of rectifying most of the lines in the image. While their method is able to correctly rectify the specified lines, it is not developed to preserve the full spherical field of view. On the other hand, our methodology is specifically developed to preserve the full spherical field of view while rectifying the lines as well as the former method. We made available our source code and results in the following link. Thank you for watching.
Thank you, Leonardo. We already have a question here from Daniel Peraza. He's asking you if you have tried other deformation functions beyond the Moebius one during your tests. Why? So essentially, why have you chosen the Moebius transformation instead of other deformation functions?
We use the Möbius transformations because they are abjection between the complex plane. They have interactivity and subjectivity, so we can ensure that the complete field of view is preserved during the transformations. Linear functions do not share this property.
Okay.
Yeah, so just like to add a little to, so this question of the field of view is very important. So Möbius transformation handle the full spherical field of view, which is key to our method, but also because they're good to specify in an interface. So with this idea of choosing 3 points over each handle, it makes it very intuitive to specify these transformations in interface. So it's practical in a variety of senses, right?
Okay. And how skilled has the user to be to use the system? You know, they have, for example, to know exactly which type of node to include in certain places or not. I mean, how sensitive is the system? You know, to the
Yeah.
user?
So the most basic goal for a user is to rectify lines. They are quite easy to identify, even if they're distorted, they are curved, but we know like what lines belong to buildings and some things like that. But there's like a limitation that if the user misses one line, so there is no guarantee that it will be rectified in the final result. So the user has to be somehow skilled to be able to not miss any line. So we rely on the user, and our experience tells us that after specifying lines on some images, the user already get skilled enough to be able to use our system.
Okay, thank you. A last question here from Thiago Silveira. Nice work. How does the Möbius induced zoom compares to real camera captures? And then he asks, where the camera is translated towards the right.
So they are, if you use a perspective projection to see the camera, you lose some information around the region of interest. So, but if you translate the omnidirectional camera to the position, like more approximate to the
So yeah, I think you're going to mute. Yeah, we're having dog problems there. So I think the main thing Lewis was telling was that when you use the regular zoom, you miss areas of the whole field of view, right? Perspective zoom is defined by reducing the field of view essentially, right? And that's our method does not suffer from this problem. It's a different zoom, right? It has this goal of preserving the full 360-degree field of view. So I would say that that's the main difference to camera captures the full spherical field, the ability to preserve the full spherical field of view.
Okay, thank you, Leonardo, for
Thank you,
the
Gustavo.
presentation. Nice to see you.
Nice to see you.
So let's move to the next presentation.
Hi, my name is Beatriz Teixeira Andrade and I'm a professor from Universidade Federal de Sergipe, Brazil. I'm here to present the paper entitled Unstructured Lumograph-Based Approach to the SVBRDF Estimation Problem. The co-authors of this paper are Benjamin Hesch and Hendrik Lensch from Universitat Tübingen, Germany, and Olga Belon and Luciano Silva from Universidade Federal do Paraná, Brazil. The appearance of materials is defined by the way they interact with light. In computer graphics, this phenomenon can be simulated using reflectance functions. In our case, we are specifically interested in the bidirectional reflectance distribution functions, which we will call BRDFs. The BRDFs estimates how much of the incoming light will be reflected and generally cover 4 dimensions, which indicates the polar coordinates of incoming and outgoing light rays at a point. So our main motivation here is to generate reflectance functions that simulate materials observed in the real world. So once these functions are estimated, we can render their appearance in virtual scenes, and we can apply this technique in the digital preservation of heritage, realistic rendering, or computer-aided design and manufacturing tools, for example. However, sampling data to generate these functions is a complex problem. As I mentioned, we have 4 dimensions. So each material should be observed from many different positions and light settings to sample all the dimensions defined by a reflectance model. So, and we have an extra issue that a surface can be composed of many materials. And this defines a variation of a BRDF that is a spatially variant BRDF that includes 2 extra dimensions that defines the position of the point where we want to calculate the BRDF. This defines the goal of our paper because we want to propose an image-based process that aims to preserve the appearance of surfaces whose reflectance properties are spatially variant. This process considers the whole environment as source of light over the area to be preserved. And we extend existing work by reconstructing the light from the whole environment to each point in this area. In this image, we illustrated the main stages of our pipeline. First, we have a data acquisition stage where we capture several images of a scene using a camera. In this case, we used an omnidirectional ladybug tree camera. These images are first used during the geometry reconstruction of the scene, and then we will trace some rays inside the scene. But first, the user needs to select the area where he or she wants to preserve the SVBRDF. In this case, it is the statue forehead. Once the area is selected, we have a ray tracing step where we will gather samples of incoming and outgoing light directions for each point in the selected area. Once these rays are defined, we use unstructured lumograph rendering to define for each ray we want to estimate the color where the ray ends as seen for the color where it starts. So these colors gave us the data we need to estimate the SVBRDF, or in more details, the BRDF of each point in the scene. So as a result in evaluation, surface patches were sampled and their SVBRDF is estimated using our method. The BRDF in each point P inside the surface of interest is defined as a linear combination of basis BRDFs. We performed experiments using datasets acquired from 2 scenes, and to evaluate the quality of the results, we performed experiments with real and synthetic data. As final remarks, our SVBRDF estimation approach uses only HDR images of the scene as input, considers that the whole environment is a source of light, and assumes that the surface does not need to be planar. These features simplify the acquisition setup and reduce storage requirements. That concludes the presentation of our work. Please feel free to write me if you have any questions, and thank you very much for watching.
Thank you, Beatrice, for your presentation.
Thank you very much.
While we wait for questions here from YouTube, let me ask you a question. Uh, Maybe 10 years ago, when I was looking this kind of problem, I, I saw a paper where the authors were trying to simulate, the, this problem altogether. I mean, they were only using synthetic data to uh, to build, these functions, to compute the luminosity and everything else. So, in our opinion, I mean, that kind of technique that only relies on synthetic data, it's much worse than the ones that use real data as well. I mean, how far they are from the real, these techniques that use real data.
Well, let me see if I understood correctly. You asked me if using synthetic data as input can be worse than real data.
Yeah, it can be
In which
much worse.
ways?
Obviously, if you use real data, you should at least get better results. But as some works, they do everything from synthetic data.
Mm-hmm.
And my question is, how worse those techniques are compared to what you are proposing here, or compared to techniques that use real data combined with synthetic data?
I wouldn't say necessarily worse, but it's a different context because synthetic data is rendered, and we use the light transport equation to generate the image that we see in synthetic data. So we have a perfect environment. Uh, the image that we generate through rendering is a perfect one. Like we don't have any noise of external factors that are not considered in the lighting rendering equation that the synthetic data will be rendered. You see, so maybe a strategy that considers synthetic data can have some nice factors, like the method per itself can be better implemented. But the main drawback that I see is that the way the data is rendered, because you don't have the wild factor, like rendering different small different light during capture. I'm not sure if I answered your question. Please
No,
feel.
no, no, no. I think you answered. We have another question here from Daniel Perazzo. Great work. So why do the images need to be HDR?
Thank you for asking, Danielle. The HDR images contains more information regarding the extremes of light conditions. Like they preserve better the very, as you can see my back here, you can see that the light is too strong over there. So if we had an HDR image, we can register better the very bright points in the image and also the very dark points in the image. A tendency of LDR images present is that when we adjust the dynamic range, we can oversaturate a bright area or undersaturate dark areas. So we aim to capture more information about color by representing the data using HDR images, so we can get a very bright, a more precise representation of brighter areas and also of darker areas.
Okay. Thank you.
Just an addition,
Sure.
just to be explicit about that, our reconstructive stage doesn't use HDR images. We use LDR, but in the other points, including the lumigraph rendering, we use HDR information that is more precise. We have 4 bytes for each channel at each pixel, against 1 byte that we use for regular LDR images.
Okay. So thank you very much.
Thank you also
Nice
very
work.
much.
Yeah.
Thank you.
So let's move on to the next presentation.
Hi everyone, I'm Rafael Ivo, and the other authors of this work are Cleto Augusto Vidal and Joaquim Bento Cavalcante Neto. All of us are from the Universidade Federal do Ceará, and I'm going to present their work entitled Improved Silhouette Rendering and Detection of Splat-Based Models, okay? So let's go. For many years, triangles are the main primitives used for discrete representations of 3D objects. However, points are also very important primitives used for modeling and rendering of real-world objects and environments. With the rapid development of 3D acquisition technologies since 2001 on Michelangelo's project, Sensor sliders use these points to detect terrain. Apple depth cameras used to reconstruct human face, and even Kinect for games. Usually, points are extended to other primitive called splats, a small circular or elliptical disk. Surface splat techniques provide high-quality rendering of points. They fill the gaps between the points and avoid aliasing by filtering approaches. Despite all that, artifacts are still noticeable on model silhouette and sharp features. Even using a better shading technique, those artifacts persist. Our proposal is to use curved splats close to the model silhouette that we are calling these primitives as quadric splats. Usually, a content creation pipeline of point clouds begins on a pre-processing step, where acquisition and denoising steps are performed. The methods proposed in this paper are located after those initial steps. Thus, consider a point cloud without noise after a pre-processing. We propose an approximation error computed for each point before a subsampling technique used to create a splat cloud. After that, our silhouette detection method is performed on object space, and the detected splats are rasterized as quadric splats. The others are rasterized as flat splats. In this video, I'm comparing the rendering of the same splat cloud of the fertility model using only flat splats and only quadric splats. Both splat clouds shown here have uniform sampling distribution of circular splats. Note the better looking renderings of smoother silhouettes when quadric splats are used. If I subtract the images, we can see that the difference happened mainly in the model silhouette, even in low curvature surfaces as we can see. Here's the distribution of the samples of the model, and here the rendering without any silhouette detection. Now, when sigma is equal to 1, only the splats that have part of their surface facing away from the camera are rendered as quadric splats. Again, this value is sufficient to remove backface splats. However, some splats that are near to the silhouette are not going to be detected, and they will be rendered as flatted splats, causing artifacts to appear at the model silhouette. That can be seen if you attempt to the back of the head and on the arms of the fertility model. The higher of value of sigma, the more splats are detected as belonging to the silhouette, decreasing the likelihood of appearing artifacts on the silhouette, at the cost of some rendering efficiency, of course. However, our silhouette detection adds less false positives, making the technique easier to control than others on the object space. For example, there are few silhouette detection methods for splat clouds on object space. The simplest is normal thresholding, where the splat is considered as belonging to the silhouette if its normal on the splat center has an angle with the viewing direction less than a certain value. In this comparison of the head model, we can see that normal thresholding can simultaneously over-detect in low curvature regions and under-detect in high curvature regions, where the most visible artifacts appear. Thus, it's virtually impossible to define a fixed threshold that can correct both types of error. On paper, I show in details the performance analysis. In summary, rendering with quadric splats has a speed rendering slightly lower than rendering only with flat splats, due to the silhouette detection and the quadric surface recasting. But since the good renderings with low sampling models can be achieved, rendering models with low sampling can be done with better speed rendering and lower graphic memory usage. And in this table, it can be seen that silhouette detection accelerates the rendering speed by up to 16%, depending on model and image resolution. Thank you all. Any questions, send me an email, okay? Goodbye.
Thank you, Rafael, for your presentation. Nice work. And I have a question for you. Are you using, I believe you are using normals to compute the silhouette? No? And my question is, are you assuming the normals are provided, no, together with the points, or are you computing the normals on the fly? And in this second case, how are you computing the normals? You are muted. Sorry, Rafael.
Sorry.
Yeah.
Normally, point clouds are subsampled to splat clouds. So each splat has a subset of points under that splat. You know, a disk and a lot of points with normals for each splat. With these points and normals, I compute a normal field, a normal vector function for each splat. So each splat has a function of normals. With that normal function, I compute the quadratic surface of each splat. And if part of this splat is facing away from the camera and part is from facing away, facing to the camera, I set that splat as a silhouette splat. You know, in part of the presentation, I talk about sigma parameter. That sigma parameter, if it's one, just remove back facing splats is sufficient. However, I compute the sigma is a scale parameter that I apply to each splat just for silhouette computation. You know, I enlarge the splat. If that enlarged splat are on the silhouette, I set that splat as a silhouette sample and 100 as a quadratic splat. If you don't, I had a 100 as a flat splat, as a normal splat, a disk, common disk, you know.
Okay. We have a question here by Vinicius da Silva. He is asking about the scalability of your method and how large the point clouds can be if you are running out of core or GPU only, and if you are using any spatial data structure to support or speed up the computation.
All these images are constructed in the GPU. You know, the silhouette detection is performed on the vertex shader, and the quadratic splat, the ray casting on a quadratic surface on these quadratic splats are performed on the fragment shader. So I can have a point cloud with millions of points, and previous the renderization, I compute a splat cloud with 20,000, 50,000 splats. So with this reduction, I can render the splats very efficiently. With the, of course, depending of the resolution of the image. If you have a larger resolution than a HD or 4K, maybe the rendering is lower, but normally the rendering is real time.
Okay, and Daniel Perazzo is asking you which GPU are you using?
My GPU is not the top, but I'm using a GPU GeForce 940 MX from it's a 4 years ago. the GPU is not the top of line, but I think the results are far better if I'm using a GPU of nowadays.
Okay. Thank you very much, Rafael,
Thank
for
you.
your presentation. Nice work. Let's move on to our final presentation.
Hello and welcome everyone. My name is Felipe Kerstin and I am going to present the domain transform for spherical geometry images, a filter designed for smoothing triangle meshes represented as spherical geometry images and at the same time preserving the mesh's important curvatures. I will first describe how the filter works and end by showing some results. This work was done by me and Eduardo Gastal. We present a new filter capable of smoothing polygonal meshes like the one shown here. Our filter has two main goals. One is the ability to remove noise from corrupted meshes, and the other is the maintenance of the important curvatures of the original mesh. As an example, you can see to the right what happens if the noisy mesh is filtered without considering its curvature. The noise is removed, but some curvature information is lost. In contrast, we show in the middle the result obtained from our filter, considering the original mesh curvature. How is a triangle mesh filtered by our filter? The first step is to convert the mesh to a spherical geometry image. Spherical geometry images are a special type of geometry image, which are images capable of representing a mesh. You can see here how a geometry image looks like. The second step is to filter the geometry image. This is done by our filter. Our filter is based on the domain transform filter, which is a filter capable of smoothing images while keeping its important edges. The domain transform filter was adapted to preserve the mesh's curvature instead of the image edges. The result of the filtering step is another geometry image. The resulting geometry image can then be decoded as a triangle mesh for rendering. Besides the spherical geometry image, our filter receives three user-defined parameters. The first one is the spatial factor. Higher values lead to higher intensity mesh smoothing. Next, we have the range factor. Lower values lead to greater curvature preservation. Lastly, we have the number of iterations. It can be used to control the trade-off between computation time and filtering quality. We proceed showing our complete filtering algorithm. Please refer to our paper to understand how each step works in detail. First, we begin by computing the feedback coefficient of each filter iteration using these equations. Then, we compute the normal buffer using Gurad's method. We smooth the normal buffer, and then we compute the domain transforms from the now smoothed normal buffer. These were all the pre-processing steps. Now we start the iterations. For each filter iteration, we first apply the subfilter H, and then we correct the periodic boundary. Next, we apply the subfilter C, and again we correct the results. Similarly, we apply the subfilter V and correct the results, and we apply the subfilter U and correct the results. Now we present some results. We start by showing a noise mesh filtered with our filter. To the right, you can see what happens when the mesh is filtered by a conventional smoothing filter that does not consider curvature information. In the middle, we show the result obtained from our filter. Note how the curvature was better preserved, and at the same time, the noise was removed. We also show an example of removing noise from a mesh obtained from scanning. This is the original mesh, and this is the result after being filtered by our filter. The total filtering time was less than 1 second for about 1 million vertices. You can see in this amplified image how the noise was successfully removed by our filter. You can also see on the top that the important curvatures were preserved, as expected. This table shows the total computation time of our filter and 4 others when filtering 4 different meshes. The other filters are the bilateral mesh denoising, the non-iterative feature-preserving mesh smoothing, the bilateral normal filtering, and the guided mesh normal filtering. For each mesh, we generated 3 different filtering results based on 3 different configurations, the fast, the medium, and the high-quality configurations. Note that our filter is the fastest one in all scenarios. Also note that here we are assuming that the spherical geometry image is already available to be filtered. We conclude the presentation by summarizing our contributions. We have extended the domain transform filter to make it applicable to spherical geometry images. This is the first demonstration of a domain transform-based filter applied to the problem of polygonal mesh filtering. We adapted the domain transformation for preserving important curvatures. And finally, when the polygonal mesh is already a spherical geometry image, the filter is very fast, providing results in linear time. This work was sponsored by CAPES and CNPq Brazil. Special thanks to the Institute of Informatics of the Federal University of Rio Grande do Sul and to the anonymous reviewers that helped to improve this work.
Thank you, Felipe, for your presentation. Nice
Thank
work. We have a question here from Daniel Perazzo again. The question is, do different kinds of noise have different performance on your method?
Good question. We actually did 2 types of tests while we were developing this work. We tested a lot with synthetic noise, meaning that we would have regular noise distributed through the mesh, And in this scenario, we were able to get very good results. And apart from that, we also tested with a real mesh, as we showed in the presentation. And well, then we are of course dealing with real noise, right? And the filter was also able to perform very well in this scenario, as you could see in the images. So this was basically the two main noise scenarios that we tested while we were developing this work, and the filter was able to perform well in both scenarios.
And I have a question for you. In terms of quality, obviously you have shown that in terms of computational performance, the method is much better than the others, but in terms of quality itself, have you tried some of those metrics that compare the quality of the result? And
we have. We didn't show in the presentation because we had only 5 minutes, right? But in the 15 minutes presentation and also in the paper itself, we present more metrics, and one of them is related to the quality of the work. And we can see in the numbers that the quality is also very good. It's comparable to the other works, and visually is also very good. So at least in my personal opinion, at least at looking visually to the mesh, I can say that the quality of the mesh is kind of similar to the other works, but our method gains a lot with regards to the timing.
okay, that's clear. And a final question here from Vinicius. Do you think it can be used to generate on-the-fly level of detail for real-time applications?
Yeah, very nice question. That's a good point. And this is one of the main objectives of our work, because we based our filter on the domain transform filter, as we said in the presentation. And the domain transform filter is a bilateral filter that is very, very fast and allows you to actually perform filtering in real time, as you stated. And for this reason, since our filter is also based on the domain transform filter, this is possible. And in fact, we actually developed a application during this work whose source code is actually available in GitHub. And the user is able to perform a filtering in real time just by clicking a button, and the mesh is filtered very fast. The only thing that needs to be accounted for is the fact that in order for you to perform filtering in real time, you already need the spherical geometry image to be available for you, because the process of generating a spherical geometry image from, let's say, a normal mesh that is stored, let's say, in the wavefront format, for as an example, this is a slower process, and this is not addressed by our work. This is addressed by the original geometry image papers, right? And if you account for that, for the generation of the geometry image, then you may not be able to do the filtering in real time. But if you already have the mesh represented as a spherical geometry image, then you can filter it as many times as you want in real time. The results, they should be very, very fast. We showed in the presentation a mesh that had 1 million vertices, and we were able to filter it in less than 1 second, right? So yeah.
Okay, Daniel, thank you very much. Congratulations for the work for you in the stall. I believe that this concludes our section, and I hope that everyone here has enjoyed very nice works. Thank you very much for attending.